Can I say a very warm welcome to our very first Peake Lecture. A particular welcome to students from neighbouring schools, from St Olave's, Darwick and Harris Garrard School. Thank you to the parents and to the Chislehurst Society for coming tonight, and of course to our own students and our own parents. You are all very welcome. I should say there are no planned fire drills tonight, so if the bells sound halfway through, please would you evacuate through the double doors on your right, on my left, and we'll all assemble outside. Now the housekeeping is over. Can I say very welcome. This is our first lecture, and it's an important time. This is our 180th anniversary since the founding of the school. We first opened in 1842 as the School for the Sons of Missionaries. This year marks the 110th anniversary that we were here on this site, and the 10th anniversary of the Gerald Moore Gallery that you've just walked through. We have a number of events and celebrations during the course of the year to mark those anniversaries. But what we wanted to do is to establish a proper lecture series that we hope will go well beyond this year and will last for many years, hence the Peake Lectures. We hope it'll become a regular fixture in school and will cover things like the arts, sciences, humanities, the social sciences, and with speakers from the worlds of sport, music, art and drama. Of course, rather like the BBC Dimbleby Lectures or the Reith Lectures, you can see how high we were aiming, we had to name this. Now we considered a number of options. Eric Liddell, after whom the Sports Centre is named, one of our most famous old boys. We decided actually to leave that. Gerald Moore Gallery, we already have the Gerald Moore Gallery, so we opted instead for Mervyn Peake. Mervyn Peake himself was the son of a missionary in the Far East. Born in 1911, he came here in the 1920s, where his writing talents were spotted very early by his English teacher, Mr. Drake. He went on to become one of England's leading writers, artists, poets and illustrators. He's best known for his trilogy, the Gormenghast series, and these books are sometimes compared to J.R. Tolkien's great novels. But instead they were more influenced by the writings of Charles Dickens and Robert Louis Stevenson. Peake also wrote poetry and literary nonsense verse, as well as short stories and radio plays and stage as well. He went on to become an accomplished painter and illustrator during the 1930s and 40s, and his friends included people like Dylan Thomas and Graham Greene. Today his works are included in the collection of the Natural Portrait Gallery and the Imperial War Museum and the National Archives. And you can see one of his sculptures if you go to the old library, and his self-portrait hangs outside our library. In 2008, the Times named Peake amongst their top 50 greatest British writers since 1945. He died in 1968. Mervyn Peake was a prolific author and poet who wrote broadly as he tried to make sense of the world as he saw it around him. And so it seems fitting for me tonight that our inaugural Peake Lecture should be given by Professor Harry Cliff, a particle physicist at Cambridge University who is seeking to make sense of the world around him in a very different way. Can I say how delighted, Dr. Cliff, we are to have you here tonight. I'd like to hand over now to Mr. Whitaker, our Head of Science, to make an introduction. Thank you.
Thank you very much, Headmaster, and welcome to all of you. As a Head of Science here at Dalton College, I'm delighted that the first of the Mervyn Peake Lectures is going to be from a scientist. And especially during Science Week, as it is this week. This exploration of ideas that you're going to hear very soon is certainly something that Mervyn Peake would have approved of. And the idea of that love of learning and the creativity that he would have espoused is certainly happening here at Dalton College. In 2022, in 2 weeks' time, this year, we will be inaugurating and bringing in our 2 new science labs in the senior school and the brand new science labs and opening them in the junior school as well. So that investment in that love of learning and that learning journey continues. Growing up in South London, Dr. Harry Cliff here was in fact an Olavian. And I'm delighted that many of your students from this year, of course, have come to join us. So that's wonderful to hear. A curator at the Science Museum, a researcher at CERN as a day job, at the LHC, the Large Hadron Collider Beauty Project, which is fantastically named, I love that. He is, of course, a science communicator. and a fantastic one at that. Those of you who've seen his online lecture at the Royal Institution, those who've watched his TED Talk, which has over 3 million views, please do go and enjoy those as I have. Like Peake, he's also a writer, and soon we'll be hearing a little bit more about his thoughts and his research that has gone into how to make an apple pie from scratch. I hope that the title will become very clear very soon as I introduce Harry Cliff. Thank you very much indeed, and pleasure to have you here. Over to you.
Well, thank you, Simon, for that very generous introduction, and thank you to you and the headmaster for the invitation. It's a really great honour to be here to speak to you this evening. Oh, good, it does work. So I should probably set expectations at the right level, first of all. I hope none of you here are expecting a talk about baking. So I think in hindsight, maybe this wasn't the cleverest title for a book. I thought it was very clever, but I think it may have led to some confusion. So as Simon said, I'm here to talk to you about really the topic of the book that I've just written, which isn't about baking, at least not in the traditional sense. It's really about where does the physical stuff that we are made of, the stuff that makes up the world around us, where does it come from and what is it made from? And these questions are at the heart of modern physics, particularly at the heart of the subject that I do my research in, which is particle physics. So over the next 45 minutes or so, I'm going to take you on a sort of historical tour from the very earliest understandings of matter right up to the leading edge of where we are at the Large Hadron Collider today, and to try and answer this question: how do we make an apple pie from scratch? So I'll start by explaining perhaps the title. So why how to make an apple pie from scratch? Well, it was actually inspired by this man. So the guy on the right-hand side wearing the very fetching red turtleneck, that's Carl Sagan. And Carl Sagan was an American astrophysicist, a very eminent scientist, but most best known as a science communicator, particularly on television. So he was, I guess, the sort of the first real sort of Brian Cox-like figure. And in 1980, he released a big-budget documentary series called Cosmos, which some of you may have seen. And at the start of episode 9, there's this rather strange scene where it begins in what you think is a shot of a planet floating in space. And as the camera zooms in, you realise it's not a planet, it's an apple. And the apple gets cut in half, and it switches this rather strange kitchen scene where apple pie is being made with this score that sounds like it's out of Blade Runner. Being the 80s, there's lots of synth music. In fact, actually, I think the score was written by the same composer as who wrote the score for Blade Runner. And then it cuts to this scene, which is Carl Sagan sitting at the head of the high table in Trinity College, Cambridge, and this apple pie is brought out to him, put down in front of him, and he looks at the camera with a little twinkle in his eye and says, and apologies for the accent, "If you wish to make an apple pie from scratch, you must first invent the universe." And the point that Sagan's making is that even an object as mundane as an apple pie, if you want to know ultimately how to make this object from scratch, you need to understand the entire history of the universe. And he uses this as a jumping off point, actually, to talk about where do the chemical elements in an apple pie come from. And he begins his story. I should first of all say, so that the story that I'm going to be telling you this evening is essentially the story of the universe, but rather than starting at the Big Bang and coming forward to the present day, we're going to be starting with an apple pie and working our way back towards the Big Bang. And Sagan actually begins the episode. The first thing he does is he stands up and he picks up a knife, and he cuts into the apple pie and he says, suppose I cut a piece out of this apple pie, and then I cut that in half, and then I cut it in half again. How many slices until I get down to a single atom? Well, the answer is about 89 or so slices. And this question that Sagan is posing is at the heart of what is arguably the most powerful idea in modern science, which is the idea, the atomic hypothesis, the idea that the world around us is made of indestructible building blocks. Deep, deep down, eventually you reach something fundamental from which everything else is made. Now, the person who is credited often with the idea of atoms is an ancient Greek philosopher called Democritus. So I certainly remember when I was taught chemistry at school, when they first introduced the idea of atoms, a picture of Democritus, a big beard, appeared on the screen. Now, to be honest, I have to say, I do think Democritus is hugely overrated, as an experimental physicist anyway, because all he really did was think, okay, do we think that if you keep cutting things in half, you get to a point where you can't cut any smaller? And he sort of went, yeah, probably. But he didn't actually check this idea. I mean, to be fair to him, the technology didn't exist for him to check it, and in what it was, the 4th century BC. But actually, I think the person we should really give the credit to for the modern concept of the atom is this man. This is John Dalton. And John Dalton was the son of a weaver, Quaker family in the northwest of England. He was born in the late 18th century. And Dalton was really the first person to take the idea of the atom that had been inherited from the ancient Greeks and make it useful scientifically. In particular, he realized that the way that different chemical elements react with one another in fixed proportions was indirect evidence for the existence of atoms. And he really was the person that set this whole journey off. And indeed, the story of him is in the book at the beginning. And thanks to Dalton, Dalton's theory basically was to say that at the time, there were a certain number of chemical elements that were known. By the end of the 19th century, there were about 90 or so chemical elements, from hydrogen all the way through to uranium. And Dalton's theory says that for every chemical element, there is an atom. And each atom for each element is different, it's indestructible. They were created somehow at the beginning of the universe, probably by God, and they have remained indestructible and consistent throughout the whole history of the universe. And so this may sound sort of quite a kind of a large number of ingredients, 90 or so, but actually it's not really when you think about it. If you think about the world we live in, it's this incredible variety of stuff. We have, from stars to liquid water to human beings, mountains, living things. And to explain all of this from just 90 building blocks is really quite impressive. But of course, at the end of the 19th century, it's realized that these 90 or so apparently fundamental ingredients are not, in fact, fundamental. And the key discovery is made just at the last few years of the 19th century. In 1897, another scientist called Joseph John Thomson, who's the head of the Cavendish Laboratory in Cambridge, where I work today, although in a slightly less, I now work in a 1970s brutalist building, whereas Thomson was working in this nice neo-Gothic laboratory in the centre of town with close access to cafes and stuff. What Thomson did was he essentially used a small glass tube, something you could just fit on a tabletop, and by doing very clever experiments, by manipulating beams of particles with electric and magnetic fields, he demonstrated the existence of a particle smaller than the smallest atom. And he called this particle the corpuscle, which you may not have heard of. That's because it was later renamed the electron. So this is the first subatomic particle. And over the next few years, the start of the 20th century, through doing experiments, first of all by using electric fields to tear atoms apart, and later using radioactive elements to basically fire projectiles at other atoms and knock bits out of them, this modern view of the atom, a more modern view that we probably most of us learnt in school, which is that the atom is a little bit like a miniature solar system. The electrons are like the planets, and they orbit around this central nucleus, this red blob, which is positively charged. So this positively charged nucleus that attracts these negative particles that go around it. And with this picture, we can start to explain the patterns in the periodic table. So if we go back to the periodic table, the way that Mendeleev arranged the elements, you notice there were certain patterns in the way that they reacted or behaved, and these patterns were now beginning to be understood in terms of the structure of atoms. Now, in the 1920s and 30s, more advanced experiments start to be done. First of all, using radioactive elements, but later actually very early versions of particle accelerators, like the one that I work on at CERN, the one that would have fit in this lecture theatre rather than being the size of a city. And essentially by firing projectiles at the nucleus, physicists realized that there were smaller things inside it that you could knock out of the nucleus. And these particles are known as protons and neutrons. And the proton is a positively charged particle, the neutron is neutral. And with this picture now, you have this picture of atoms as being made of just three particles, the electron, proton, and the neutron. So you've reduced this picture of 90 or so fundamental ingredients down to just three. And this is one of the reasons that I remember learning this in school and just finding this incredibly beguiling. It's so exciting, I think, this idea that you can reduce all the complexity in the world to something really, really so simple. And it's also great because a lot of physicists, actually, if I admit it, are quite lazy. And we don't really want to remember 90 things. 3 things is much better. 3 is about what we can manage, really, actually. And with these 3 ingredients, you can start to understand the different chemical elements. So hydrogen, the simplest element, 1 proton, 1 electron. Helium, the next simplest, 2 protons, 2 neutrons, 2 electrons. And then carbon, an element that's crucial for life, 6 protons, 6 neutrons, and 6 electrons. And the way the electrons arrange themselves around the atoms explains their chemical properties. You start to have a deeper understanding of matter. The other thing this picture does is in about the 1920s, when this picture is starting to emerge, it allows physicists to ask a question that was previously not possible to ask, which is, where do atoms come from? And when Newton, who was another person who sort of thought about the idea of atoms, Newton hypothesized, that he was obviously a deeply religious man, and he said, it seems to me that in the beginning God formed atoms, these imponderable, massive, hard objects, and they've existed ever since. So God made them, and they're otherwise impervious. We now know they're made of smaller things. Well, that suggests the possibility, at least, of making them, of them being produced somewhere. And the obvious place to begin is with hydrogen. You say, well, hydrogen is the simplest element. So is there a way, perhaps, of combining hydrogen together to make the other elements? And Arthur Eddington, who is the head of the Astronomical Observatory in Cambridge, is one of the first people to start to think about this problem. I promise you I'm not being Cambridge biased by only mentioning Cambridge people. But anyway, Eddington, the problem is trying to bring hydrogen together, say, to make helium. The problem is you have the centre of hydrogen atom is positively charged. You try and bring another one towards it, what happens is, well, they repel each other. They like charges repel. And actually, Eddington calculates that in order to get an atom to fuse together, to sort of get close enough that they can join, you need those atoms to be going incredibly quickly. And he works out that actually you need temperatures of tens, if not hundreds of millions of degrees. And the question is, are there places in the universe where temperatures like that exist? Well, Eddington is an astronomer, and he thinks there is. He's the first person to build a realistic model, theoretical model of a star. And using his model, he calculates the temperature at the centre of the sun is something like 20 million degrees, which is about the right temperature, hot enough for protons to overcome their repulsion and fuse together. So we start now, through the discovery of subatomic particles, to also be able to start to ask the question, where does the matter around us come from? Where does the carbon, if you like, in our apple pie ultimately come from? Now, there's actually quite a funny line, because there's a big debate about this in the astronomical community, and some people are arguing that even the sun actually isn't hot enough. And Eddington famously writes down, he gets very upset by this, because he's sure that stars are the places where the atoms are made. And he said, to the critic who says that stars are not hot enough for the fusion of the chemical elements, I suggest they go and find a hotter place, which is possibly the most genteel way anyone's been told to go to hell. So we now know, actually, from a variety of different sources, theoretical but also not astronomical, that in the centre of the sun, at temperatures of about 15 million degrees, hydrogen is indeed fused together to make helium. Now that's great, but there isn't actually any helium in an apple pie. So we need to go a little bit further than that. So how do we get, say, to the next element, carbon? Carbon, essential ingredient for life. Well, this is actually a picture of where a lot of the carbon in our apple pie comes from. So this is a picture of something called a planetary nebula. It's actually the bow tie nebula, which is essentially what it is. This is a vision of our own solar system about 5 billion years from now. So what will happen in the future is the sun is continually burning hydrogen in its core, converting it into helium. And as it does so, that's where the heat that makes the sun shine comes from. There will come a point where the entire core, or most of the core of the sun, will have been converted into helium, and there's no hydrogen left. And when that happens, the sun's fuel source runs out, and the core starts to collapse in on itself. And as it does, it heats up. The sun swells to an enormous red giant, will consume Venus and Mercury and probably Earth and Mars as well. And then it will ignite. Well, as the core collapses, it gets hotter and hotter, and eventually temperature becomes high enough for helium to start to fuse together. And there's a reaction basically that transforms 3 helium nuclei colliding simultaneously into carbon atoms. And so eventually, at the end of its life, our sun will start to produce carbon, and once the center of the sun is turned into carbon and oxygen, the reaction will stop. The sun will die, it will waft its outer atmosphere into space, which is what you can see here, this big cloud of luminous gas. That's the bulk of the star that's blasted out of it at the end of its life. And at the very center of this image, which you may just about be able to see, there's a little white point. And that is essentially all that's left at the end of the core of the star. It's what we call a white dwarf. It's sort of like the dying ember, about the size of the Earth, but with temperatures of millions of degrees, gradually cooling. And in this big cloud of gas, not only do you have the helium that the star's made during its life, but also large quantities of carbon. So in fact, most of the carbon in your bodies and in the world around us and in the apple pies we eat came from the death of a star, much like our own sun. Now, that's good, but there is a bit of a problem. So there are other things in our apple pie too. There's nitrogen and there's oxygen. And actually, while our sun will actually make oxygen at the very end of its life, the oxygen ends up locked inside the white dwarf. It can't get out into the rest of the universe. So it can't end up mixed together with other elements to make other things. So if we want to find where the oxygen comes from, we need to go to a different source. And this is actually an image of the kind of place that the oxygen in the world around us came from. This is another nebula, but this is the remnants of a much more violent process known as a supernova. So this is the Crab Nebula, which is associated with a supernova that went off, I think, in the 11th century. So it was visible around the world. And a supernova is the fate of a star many times heavier than our own sun. With a very heavy star, what happens, eventually the core in the same way is converted into carbon and oxygen. But a much heavier star, gravity is strong enough to crush the white dwarf essentially in the middle of the star, crushing it to even higher temperatures. And at that point, oxygen and carbon start burning to make silicon and heavier elements until eventually the whole core of the star is converted into iron and nickel, which are the stablest elements in the periodic table. And when that happens, that's the end of the road. That's game over, because iron and nickel, as I said, the most stable elements, you can't fuse them together and release energy. And this leads to this catastrophic, inexorable collapse, where the huge weight of the star falls inwards without any heat source to keep it inflated. And what happens essentially is the star crashes down until its density at its center reaches the density of an atomic nucleus. So you've forced all the protons and neutrons right next to each other. And at this point, atoms don't like to be closer together than in an atomic nucleus, and the star effectively bounces. So it bounces off, it falls inwards, then it bounces, and as it bounces, it creates this incredibly violent explosion that will outshine every star in a galaxy for a brief period of time. And in this incredibly violent process, all the products that have been made in the center of the star get blasted out into space. So the universe gets enriched with oxygen, nitrogen, silicon, iron, many of the chemical elements going through the middle of the periodic table. So the oxygen you are breathing right now, most of that, almost all of it, came from an event like this billions of years ago in a very distant part of the universe. While I was researching this book, I had the very good fortune to go on some really exciting visits. My favorite one, I think, of all was a visit to Apache Point Observatory in New Mexico. So this is an astronomical observatory on top of a mountain, 3,000 meters up above the New Mexican desert. And there they use this instrument here. This is the Sloan telescope, and I'll just show you a little video of it. This is it opening up. This is a video I took on my iPhone, opening up for the observing night. It was a spectacular scene with this glorious sunset, the petal of the camera open. And what this telescope does, essentially, is it looks at the stars in the Milky Way galaxy, and it analyzes their light. And the way we know so much of this story, actually, is by analyzing the light from dead stars like nebulae and supernova, we're able to detect the telltale signatures of different chemical elements. And there are astronomers around the world who work on a sort of detective puzzle of trying to figure out, based on looking at stars through various points in their evolutionary history, the story, ultimately, of the chemical elements and where they came from. And this story is actually by no means finished. There's still big discoveries being made. And one of the astronomers I spoke to, Jennifer Johnson, who's at Ohio State University, she produced this rather lovely image of the periodic table. So this is the periodic table where the colors represent where the different elements came from. So you can see, I can tell you, check I'm not lying, where are we? So where's carbon? Carbon's up here. So you can see carbon is mostly shaded in yellow. So that's from dying low-mass stars. So that's basically our sun. Our sun is a low-mass, quite a small low-mass star. Whereas if you go a couple of rows across, columns across to oxygen, you'll see almost all of that comes from exploding massive stars, in other words, supernovae. But I said this isn't a done deal. And actually, one of the really interesting things, when I was at university, I think even, I was taught that the heavy elements, so things like gold, where's gold? Somewhere. I shouldn't try and do this live. AU, can anyone see AU? 79, there we go. Gold and platinum and silver. It was thought that these elements came from supernovae. But actually, just in the last few years, that's changed. And that's thanks to an amazing discovery that was made back in 2017 by an instrument called LIGO. Now, LIGO is a telescope, but it's a very strange telescope. In fact, it's the first telescope of its type. And it doesn't look at the universe in light. It looks at the universe in something called gravitational waves. Now, gravitational waves are quite a hard idea to get across, so I won't really try and get them across, but suffice to say, basically what they are ripples in space and time. That probably doesn't make any sense, but just take it on trust. And these gravitational waves, they're produced by incredibly violent processes, and what LIGO detected in 2017 was a gravitational wave produced by the collision of two objects called neutron stars. Neutron stars are actually a possible endpoint for a supernova. If the supernova is of a certain size, but not too heavy, what happens is this core of the star ends up basically as a giant atomic nucleus, about the size of London, 30 kilometers across, but weighing as much as the sun. So incredibly dense. They're basically like just a giant nucleus made only of neutrons. And what LIGO detected was two of these very dense, smallish objects spiraling around each other and then colliding. And when they collided, they created these ripples in space-time that traveled out through the universe and eventually millions or billions of years later were detected by this telescope on Earth. And when LIGO detected these waves, it put out an alert because what LIGO had seen up to that point was the collision between black holes. So these black holes are, even if you have a heavier star, that's what you get. But when a black hole collides with another black hole, you don't get any light. It just goes bloop. It kind of makes a bigger black hole and that's it. Lots of gravitational waves, but nothing else. Neutron stars, on the other hand, this like colliding two diamonds or something. They're incredibly dense, hard objects. When they smash into each other, they create a huge amount of light. And LIGO told optical telescopes around the world, we think there was a neutron star collision somewhere over there. Have a look. And when the telescopes looked, they saw a glow of light. And when they analyzed the light, they saw telltale signatures of gold and platinum and a lot of the other heavy elements. And they realized that it was these events, these incredibly violent collisions between neutron stars that are responsible for making most of the precious metals. So if you're wearing a piece of jewelry, you are basically wearing a piece of neutron star. And they calculated, actually, interestingly, that in this collision, it made something like 30 solid gold planet Earth's worth of gold. Now, before you get onto Elon Musk with a get-rich-quick scheme, I should say this happened several billion light years away, so it's not really a practical way of making money. But anyway, it's kind of an amazing, amazing thought. And so, as I said, this is still a story that's being told. So from astrophysics, from nuclear physics experiments and laboratories and from astronomy, we've discovered a lot of the story of where the elements come from. But there was a bit of a mystery. If you go back, this story was being pieced together in the 40s and 50s and 60s, most of it, although not the neutron star stuff obviously much more recently. But there was a big problem actually with this idea that the elements come from stars. And it comes from when you look at what the universe as a whole is made from. So this is a pie chart, appropriately, representing the chemical makeup of the universe. So you can see the vast majority of it is hydrogen, 73% or so. And then you've got the other elements, carbon, oxygen, everything else is just this little sliver, and then the rest is helium, about 25%. Now, if the universe began as pristine hydrogen, and stars had been fusing that hydrogen into heavier elements, there's a bit of a mystery here, which is, why is there so much helium and so little of everything else? Because, even our sun, which is a low-mass star, it makes helium, but it also then makes carbon and oxygen. So you'd expect there to be much less helium and much more of these guys. And it was realized that actually there is another furnace, another oven, if you like, in which the elements are made. And it's, in a way, the greatest oven in history, which is the fireball of the Big Bang. So it was in actually the fireball of the Big Bang, the beginning of the universe, that we now believe that most of the helium in the universe was made in a very short space of time. So if you go back to the very earliest moments of the universe, we now believe, thanks to observing the fact that the universe is expanding, that in the past it was far smaller. And if you go back 13.8 billion years, the entire observable universe was concentrated into a volume much, much smaller than an atom, and it was incredibly hot. And after the universe began, there was a period of about 15 minutes when the temperature of the universe was hot enough to fuse protons, hydrogen nuclei, together to make helium. So you had this almighty cooking process that took place over about 15 minutes, where about 25% of the universe was converted into helium. And that was essentially, that mixture of helium and hydrogen, the little bit of lithium as well, is what ended up filling the universe, and then from which the first stars formed, which then created the other elements. So we actually need these two different ovens, the stars themselves and then the fireball of the Big Bang. So we can now ask another question. So we can now see that, the elements are made by fusing protons and neutrons together. But this now allows us to ask another question. Well, okay, if you want to be really bloody minded about it, and if you're a physicist, you are, where do protons and neutrons come from? Now, until the 1960s, it was thought that protons and neutrons were fundamental particles. They couldn't be broken down into anything smaller. But in 1964, an amazing experiment was done, and it was done in California at a particle accelerator called the Stanford Linear Accelerator, which is essentially a 3-kilometer long electron gun. And what the Stanford Linear Accelerator did was it fired electrons very close to the speed of light down this very long trackway and fired them at protons and neutrons. And what they found was, by looking at the angles that the electrons bounced off the protons and neutrons, they were able to discern that there were actually smaller things inside protons and neutrons. It was a bit like taking an X-ray of a proton or a neutron. And it was realized that these particles that had been thought of as being fundamental were not fundamental. They're made of smaller things, and we call these smaller things quarks. Quark is it was a nonsense word invented by Murray Gell-Mann, who was one of the theorists behind the idea of quarks. It's actually from an incomprehensible novel by James Joyce called Finnegan's Wake. Anyway, quarks or quarks, depending on your taste. And there are 3 quarks inside a proton and 3 inside the neutron. And in fact, there are 2 types that are important. There's something called an up quark, which has a positive charge, and then something called a down quark, which has a negative charge. By combining these things together, you can make your protons and neutrons. And they're held together by these other particles called gluons, which are sort of like these sticky strings that hold the quarks together. So again, we now have a new understanding again. We have this understanding that protons and neutrons are made of smaller things. And we can now ask the same question that Eddington asked in the 1920s, which is, okay, if protons and neutrons are made of smaller things, where did protons and neutrons come from? How did they get made? Well, the answer is during the Big Bang. And if you go back to around a millionth of a second after the Big Bang, the universe had a temperature of around 100 billion degrees, so incredibly hot. And under those conditions, normally quarks are held together by gluons very strongly. So the strong force, the force that holds quarks together inside protons and neutrons, is incredibly difficult to overcome. But at these very high temperatures, this force cannot hold quarks together. And if protons and neutrons effectively melt, and they turn into this very strange substance. It's a state of matter known as a quark-gluon plasma, which is essentially like a kind of the hottest soup you can think of. It's a sort of superheated, superfluid, made of free quarks and gluons flying around. This is at least the idea, but one of the amazing things is that actually, routinely, we can make this state of matter now here on Earth. And it's done at a machine called at Brookhaven called RIC, which is a big particle accelerator. And what they do at RIC is they fire gold atoms, believe it or not. I don't know why. I think because it's got lots of protons and neutrons in it, so it's good. Presumably they don't use very much gold, else it'd be very expensive. They fire gold atoms around this ring. They're accelerated and they collide them into each other at very high speeds. And when they collide, they briefly recreate the conditions that existed in the universe about a millionth of a second after the Big Bang. And in the 2010s, this experiment was able to prove that it had, for the first time, created, for a fleeting moment, this quark-gluon plasma. And what you can see here is actually, this is an image of one of those collisions between 2 gold atoms. It looks like a complete mess, but basically this is a cross-section through the detector, where the collisions happen. The detector, you can think of as like a barrel shape, and the collisions happen in the middle. And what happens is the gold atoms collide, they briefly create this superheated blob of liquid, and then the liquid cools down, and it sort of almost like freezes, a bit like a liquid turning into a solid, and it turns into particles, protons and neutrons and other things, and they come flying out. So you can see there's thousands. These lines are individual trajectories of different particles that have come out from this collision. So they're incredibly messy things to analyze, but by looking at the ways, the energies, the directions of these particles, the scientists were able to infer that they had indeed created this primordial state of matter, which is the stuff that filled the universe in the first millionth of a second after the Big Bang. So this is really sort of what we think the world is made from today. 3 particles, the electron, the up quark, and the down quark. And so everything in the universe, at least the observable universe, from stars to apple pies to you and me, we are just made of these 3 different types of thing. which is kind of incredible, given how varied the world is. But it doesn't stop there. Of course, we don't want to stop there. Can we go further than this? Can we ask, where do these things come from? Why do they exist? Where do they come from? Well, we can. And one of the strange things about particle physics, and I'm a particle physicist, it's sort of, in a sense, it's a subject that's quite badly named, because we don't really think of particles as being the fundamental ingredients of the universe at all. What we understand to be the truly fundamental ingredients of the universe are much stranger and slightly harder to picture objects, or physical objects. They're called quantum fields, which sounds quite scary, but it's not that bad. I'll try and break it down for you. So let's start with the idea of a field. And now, a field in some sense is a kind of abstract mathematical object. Technically, what a field is in mathematics is anything that has a value in space. So you could think of, if you like, the temperature in this room as a field. You could get a thermometer and measure the temperature at every point in this room. And you imagine a huge array of numbers, which are 20 degrees over here, 23 degrees over there, whatever, a bit colder by the door. That's a temperature field in some sense. But fields are more than just an abstract mathematical thing. And we all know this, because I'm sure everyone in this room at some point in their life has picked up a magnet and another magnet. And they've pushed the two, say, take the two north poles, and you push them towards each other. And when you do that, you start to feel something. You start to feel this repulsive force. And even though you can't see anything, there's nothing, you can put your hand in the middle, nothing happens. But if you kind of trace, you can trace out the influence of this thing. And once you've done that, you can't really deny there is something physical there. It's pushing back on you. And what you're feeling is a physical thing, and that's a magnetic field. Now, if we think, so these fields exist, and we experience them all the time. But in particle physics, we go a little bit further. This is where the quantum bit comes in. So the magnetic field between a magnet is actually an aspect of a more unified field known as the electromagnetic field. It's a combination of the electric field and magnetic field, which also explains light as well. So light is a wave in the electromagnetic field. Now, in particle physics, what we actually think of as a particle is as a tiny, the smallest possible wobble in a field. So the photon, which is the particle of light, is the smallest possible wobble in the electromagnetic field. So the reason you're seeing me right now is because there are photons which are being produced in the lights, which are little ripples in this electromagnetic field that's all around us. They come across the room, they bounce off me, they go into your eyes, your brain interprets the signals. So we're sort of seeing photons all the time. But we don't just think of photons this way. So if you take electrons, we also believe, or we sort of know really, that there is something in this room, fills the whole universe, it's invisible, you can't touch it, but it's this thing called the electron field, and every electron in your body is a ripple in the electron field. And the same is true for the quarks. So the up and the down quark, there's an up and a down quark field, and the up and the down quarks are ripples in the up and the down quark field. And this is it's sort of a strange idea in a way, but it also means something quite extraordinary, which is actually that all of us are connected to each other. We are all made of the same object, which is one object. There's only one electron field. So we are all sort of, if you like, waves in the same ocean, which is a kind of, I don't know if that's a disturbing thought or a nice thought, but it sort of depends who you're sitting next to, I suppose. So this means that this view, it was thought until about the 1930s and 40s that particles, particularly particles of matter like the electron, couldn't be made. They existed, a bit like Newton's atoms, forever. With the advent of quantum fields, we now have a way of making them. And what happens is you basically have to do is put some energy into a quantum field, you make a ripple, a particle appears. So you can now make particles. And this is what we think happened in the very earliest moments of the Big Bang. And we have a theory that describes these quantum fields, and it's called the Standard Model, which is possibly the worst named theory ever. It's very boring, considering that this quantum field theory, the Standard Model, is basically the closest we've come to a theory of everything. It describes every observation we've ever made of the universe, of the material in the universe. The only thing it doesn't include is gravity. But other than that, it covers everything. The behavior of every atom, how stars work in their cores, the physics that goes on in the world around us. So it's a staggeringly successful theory. But it has some really big problems. And that's what I'm going to sort of talk to you about now. And these problems are connected very deeply to the question of where these fundamental particles, or another way, where do these fields come from? So I'm just going to give you a little health warning. So we've now got to the edge of what we know pretty confidently, and we're going off the edge of the map into uncharted territory. So the next bit of the talk, the last bit of the talk, is going to be about things that we're much less certain about, where there's a lot of speculation and possibilities that things will change in the future. So just so you've warned, here there be monsters. So this question, where do these particles come from? Well, we have this way now of making particles. You hit a quantum field, particles appear. But actually, it's not quite as simple as that. If you hit the electron field, make it ripple, you don't just get an electron, you also get something called an anti-electron, a sort of mirror image of the electron. So two particles, you don't get one particle, you get two. Two will pop out. One with a positive charge, which is the anti-electron, and one with a negative charge, which is the electron. And we know, thanks to experiments, that every matter particle that we've discovered, the quarks, the electrons, various other things, they all have anti-partners, anti-particles, which you can think of as, and actually in quite a precise way, as mirror reflections of each other. They're exactly the same in every way, particles and antiparticles. The only difference is their charges are the other way around. But this is a bit of a problem. So as I said, if you hit a quantum field, you make a particle and the antiparticle at the same time. And then if the particle and antiparticle meet again, if they come back into contact, they will annihilate each other, and the energy will go back into some other form. So they're created together, and they're always destroyed together. Now, this is a bit of a problem, because if you go back, say we go back before quark gluon plasma to a time, well, when the universe was filled with particles, and nothing else. We want to ask, well, where do those particles come from? Well, this is a bit of a problem, because in the very earliest moments of the Big Bang, you have a huge amount of energy. Particles and antiparticles are being created all the time, so continuously created, and they're continuously banging into each other and annihilating again. So you have this kind of continuous reaction going on. Now, the universe is expanding, and as it expands, it cools down. And as it cools, eventually there isn't enough energy left in the plasma to keep making more particles and antiparticles. And then something really catastrophic happens. The amount of particles and antiparticles is fixed, and as the universe continues to expand, they meet up with each other and they annihilate completely. And you get left with a universe with nothing in it, apart from a few lonely photons whizzing through the infinite blackness. So this is what the universe should look like. This is what modern particle physics tells us the universe should look like. But of course, we know it doesn't look like that. It looks like this, plus or minus some spaceships. So the existence of stuff and us and everything around us is a big problem if you're a theoretical physicist. It's kind of a bit inconvenient, actually. They would prefer a universe with nothing, because that would be nice and easy to explain. So the question is, how is it that matter won out over antimatter? Why weren't we all annihilated at the beginning of the universe? And we don't have a good answer to that question at the moment. And this is one of the big questions that drives a lot of research, both at the Large Hadron Collider and elsewhere in modern physics. So this is problem number one. How did matter survive the Big Bang? We don't have a good answer to this question. So I suppose, to give you a spoiler, we don't yet know how to make an apple pie from scratch. But we are trying to find out. I'll mention but there is also a second problem that I'll talk about, which is sort of different in character, but similar in the outcome. And it's to do with something called, which you may have heard of, something slightly scary, called the Higgs Boson. Now, the Higgs Boson, hands up who's heard of the Higgs Boson? Well, you have now, because I just said it, but yes. Hands up anyone who can explain to me what the Higgs Boson is. Oh, well, you were in the talk earlier, so that's cheating, weren't you? Anyway, well, I'll try my best to explain what the Higgs boson is. The Higgs boson is actually famously difficult to explain. It's kind of an abstract mathematical thing. People have tried to cook up various analogies to get it across. None of them are actually very good. But in essence, what the Higgs boson does is it explains why particles that we're made from have mass. Mass is this property where things have kind of, if you push on them, they push back, basically. That's what mass is. And it was, for a long time, it was a mystery as to where this property came from. Now, the basic idea is that there is an additional quantum field, another one of these invisible fluid-like substances that's everywhere, which is called the Higgs field. And this field is rather different from the other quantum fields. If you manage to go into the emptiest bit of space you can, so you went way out into intergalactic space, you built a box, sucked out all the stray atoms, all the bits of light, what you've got left there is what we call the vacuum. Now, because of quantum field theory, actually, there ain't no such thing as a vacuum anymore, because even when you've taken all the particles away, the quantum fields are still there. So this box that you've built is full of quantum fields, sort of wobbling about gently. Now, if you were to measure the energy of each of these quantum fields, it would basically oscillate around zero. So say the electromagnetic field, without any light in it, has no energy in it, zero. The Higgs field is different. The Higgs field has a constant value everywhere. It's a bit like the sort of temperature. The whole universe has been lifted to a certain level. And this energy in the Higgs field kind of makes it behave a bit like, I said these fields are like fluids. It makes it behave a bit like a kind of treacle or a molasses, some kind of thick, gloopy substance. Nonetheless invisible, but the analogy is not perfect. And what happens is when particles move through the Higgs field, this thick, treacly substance slows them down, and it gives them what appears to be mass. So they acquire their mass basically through interacting with this Higgs field thing. Now, the Higgs boson is just the ripple in the Higgs field. It's the particle that goes with the field, just like the electron is the ripple in the electron field. So that's the Higgs boson. Now, the problem with this idea comes when you try to work out why the Higgs field has this finite value. So this, as I said, it's not all the others are zero. The Higgs field is the only one that's not zero. And it's this value that's responsible for mass. If it was zero, nothing would have a mass. And we believe, according to the standard model, that at around about a trillionth of a second after the Big Bang, so very, very short time after the universe began, the Higgs field switched on. Essentially, it acquired its modern value. And the problem with this is, if you try and calculate what value it should have settled at, you get two possible answers, basically. The first is this number. Now, this number here with lots of zeros, which I think is 10 billion giga-electron volts. Now, giga-electron volt is a particle physics unit. It's basically the mass of a proton. So that's how much a proton is, 1 giga-electron volt, basically. This is a lot of energy. This is what we call the Planck energy, which is at least the highest, more or less the highest energy we can imagine, at least with our current understanding of physics. So this is a bit like the Higgs field being turned on all the way. It's a bit like, imagine you've got a dial, you've turned it right round to the end. This is a problem, because if the Higgs field was this strong, what would happen is that every particle in the universe would become so heavy that it would collapse into a black hole. And you end up with a universe with nothing in it, just black holes. And obviously in such a universe, we could not exist. We wouldn't be there. Clearly, we don't live in that scenario. So what's the other one? Well, the other one is the Higgs field is off, is at zero. And if that were true, that's also very bad, because in a universe with a zero value of the Higgs field, electrons, for example, have no mass, and atoms don't form. And the universe is just filled with a kind of haze of particles zipping about at the speed of light. But again, there's no structure, there's no atoms, and therefore there's no wobbly flesh-colored things made of atoms like us. So standard model seems to be saying that we shouldn't exist again, basically, that there are only two possible scenarios. One is the universe is made of black holes. The other is there's no structure and there's just a gas of particles whizzing about. So again, the fact we exist is a big mystery, and we don't really understand how is it that the Higgs field, this is the value it actually settled at, 246 GeV, which is weirdly specific. It's not zero, and it's not 10 billion. It's very close to zero, but not quite zero. And that's crucial. The thing that's disturbing about this is if you move the value of the Higgs field either direction, even a little bit, you very quickly end up in a universe which is uninhabitable. It seems to be a kind of Goldilocks value that's been perfectly balanced to allow us to exist. And this makes physicists very, very unhappy, because it looks really fishy. Like some cosmic tinkerer has set things up just right, and we don't like that. We would like to have an explanation for why this value is what it is and how the universe is allowed to have structure. So we have a second problem. Why didn't the Higgs field kill us? And we don't know the answer to that either. And that is why, amongst other reasons, that the LHC, the Large Hadron Collider, was built. So this is the machine where I do my day job. Well, I say my day job. I mostly sit in an office doing data analysis, but sometimes I go here. So this is a photograph taken from a plane of the area outside Geneva. What you can see in the distance, this is the Alps, and you've got Mont Blanc. This is Lake Geneva, or Lac Le Mans, and there's Geneva there. And then marked in yellow on the countryside is the route of the Large Hadron Collider. So this is the largest scientific instrument ever been built. It's a 27-kilometer circumference particle accelerator. And its job is to basically hit quantum fields very hard and make them wobble. That's what the LHC does. And it's trying to see if we can make new quantum fields wobble that we've never seen wobble before. Or put another way, we're trying to discover new particles. And the way it does this is really quite simple. Over here at CERN, there is a bottle of hydrogen gas, ordinary industrial canister that you can buy at any industrial supplier, if you so desire. And that gas is extracted, it's ionized, so it's hit with an electric field that rips the hydrogen molecules apart. You end up with protons, just the nuclei of the hydrogen. And they're sent off through a series of accelerators. They're accelerated higher and higher speeds, and eventually they're shoved into the Large Hadron Collider. They go round this ring, and every time they go past this point here, they get a kick from a 2 million volt electric field, and they're accelerated to a higher speed. They go round again, kick again, faster and faster and faster. And they go around the ring 11,000 times a second, so they're doing 27 kilometers in 11,000th of a second, which corresponds to 99.9999991% of the speed of light. So they're almost, you can't get to the speed of light, but they're very close. And then when they get to that speed, they are collided head-on inside 4 specially built experiments, detectors basically, here, 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 and here. And this is what these experiments look like. So this is one of the detectors at CERN. This is the CMS experiment, which stands for Compact Muon Solenoid. I always think it's a strange use of the word compact. So this thing, to give you a sense of scale, this is a person in a hard hat. So it's about 15 meters high, 25 meters long. It weighs 14,000 tons and contains enough iron to make 2 Eiffel Towers. And what this instrument does is essentially it's a gigantic 3-dimensional digital camera. It's like an onion, well, not really an onion. It's like a barrel-shaped onion with lots and lots of layers. And as the collisions happen right in the middle, the particles fly out, and the different parts of the detector allow us to reconstruct the trajectories, the energies, and so on of the particles as they're produced. And this is a typical reconstruction of one of these collisions. This is 2 protons buying it, basically. So they've collided head-on. And what's happening here is that the reason we accelerate these particles to very high energies, we're trying to get into a huge amount of energy, the reason is we're trying to discover new particles that haven't been made before. And the reason they haven't been made, presumably, is because their masses are higher than any machine that has been able to reach. So you have to have enough energy in your collision to make these particles. So what's happening here is the kinetic energy, so the energy associated with the motion of these particles, is being converted into new particles. So they collide, that energy sets off a kind of a vibration in loads of different quantum fields, creating new particles, and they fly out from the collision. And that's what you're seeing here. So each of these lines represents a new particle being created from the energy of the collision. And the job of people like me is to scour through, well, now I think probably trillions of these collisions, looking for the very rare events where we might have got evidence of something new happening. So this is the way the Higgs Boson was discovered, for example. So actually about 10 years, it'll be the 10th anniversary on the 4th of July this year of this moment. So this is the main auditorium at the CERN site, and this is as excited as you'll ever see physicists getting. This was a really exciting day. It was the day when the discovery of the Higgs was announced to the world. It was quite moving at the time, actually, because Peter Higgs himself, who had been a relatively young man in 1964, when he proposed this idea, was there in the room in his 90s, seen wiping away a tear. So it was quite, I think he said himself, he never expected this discovery to be realized in his lifetime. And this was a great day in many ways. And it was also, I suppose, the culmination of the story of 20th century physics. This is the completion of what we call the Standard Model, the last missing piece that hadn't been found, that had been predicted. But what it didn't do was really tell us very much about these other big questions, like why we weren't all annihilated at the beginning of the universe. And what we were hoping to see over the last 10 years was new particles being created in the LHC's collisions that could help to address some of these questions. Now, unfortunately, so far at least, the story has been slightly disappointing, to be perfectly honest. We had lots of expectations that we would be seeing new ingredients of nature, new quantum fields at these collisions. And actually, the story of the last 10 years has basically been the standard model being confirmed over and over and over again. And every search we've done has come up empty-handed. We keep just proving how brilliant the standard model is, which is frustrating because we know it's not finished. We know there's missing stuff. But I'm going to finish the lecture by just talking a little bit about something that's going on at the experiment that I work on, which is this one, LHCb. And it's kind of early days still, but we could be, perhaps, on the brink of a breakthrough that may lead us to the next chapter of this story. So LHCb, this is the detector I work on. This is the detector. It looks rather different to CMS. It's sort of arranged in like layers. It's a bit more like it's not quite as sciencey looking. It's a bit more like a multicolored toast rack or something. But anyway, the B in LHCb stands for beauty, which is the name of one of the 6 quarks. So these guys up here, these orange things, they're the quarks. And the 5th heaviest of them is called the beauty quark. Actually, I should say, most physicists call this particle the bottom quark. So when the top and the bottom quark were the last 2 to be discovered, there was a bit of an argument about what they should be called. And there were some people who said that they should be called truth and beauty, but other people said that's too poetic. Let's just go for top and bottom. And so top and bottom won out, unfortunately. But at LHCb, we'd rather be known as beauty physicists than bottom physicists, so we tend to call it the beauty quark. This is a typical collision at LHCb. It's rather different from the other one you see. That's because our collisions happen at the edge of the detector. And the reason for that is that the beauty quarks tend to just fly in one direction. So there's all kinds of stuff going over here, but we don't detect it. We're just looking for these beauty quarks that go sort of very close to the beamline. And the reason we are interested in these beauty quarks is because they are a great place to look for evidence of new quantum fields. And the way this works is basically a bit like this. So what we're doing is rather different from the other experiments. What they do is they try and hit a quantum field, make it wobble, they see the particle. We do something rather different. So we have this beauty quark. Now, beauty quarks are unstable. The reason we don't see them in the universe is they only live for about 1.5 trillionths of a second, and then they decay into other particles. So, for example, they could decay into 3 other particles. And the way this happens is through the forces in the standard model. So the forces in the standard model allow particles to turn from one type into another. And because we understand the standard model really well, we can do a very, very clever sum calculation, and we can work out how often this decay should happen, for example. But let's imagine that there is a new force of nature, a new quantum field that we've never seen before. If that quantum field, if that force interacts with beauty particles, then it can provide a different way for this particle process, this decay process to happen. So basically what we do is we look for these decays in our collisions. We count them, we work out how often they happen, make a very precise measurement of how often they happen, and then we compare that to what the standard model predicts. So you have 2 numbers of measurement, theoretical prediction. Now, if the standard model is right, they should be the same. They should line up with each other. But if there's something new that's changing the decay, they may not. They may deviate from each other. And if you see a difference between these 2 numbers, essentially, that is indirect evidence of a new quantum field. It's a little bit like if you're looking for an animal in a jungle, say an elephant. Rather than seeing the elephant itself, what you're actually seeing is its footprint. So you see the impression it leaves on the ground. So we're seeing the impression of some heavier particle that we haven't seen directly, but we're seeing how it affects the more familiar particles that we do know about. And what has been happening in the last few years is related to a particular way that these beauty quarks decay. Now, I apologize for various particle names flying around at the moment, but bear with me for a second because it's not that hard, hopefully. So we have this beauty quark, it decays, and one of the ways it can decay is into something called a strange quark, which is the next lightest one, basically. And then it spits out an electron and an anti-electron. So that's decay number 1. And we compare that decay to a different decay, a very similar decay, where this time a beauty quark decays into a strange quark, but instead of electrons, we've got something called a muon, 2 muons. Now, muons are heavier versions of the electron. They're basically exactly the same as electrons, they're just a bit heavier. And the reason this is an interesting thing to look at is because the standard model, the forces that we know about, treat electrons and muons identically. And what that means is that this decay, the one with electrons, should happen just as often as the one with muons. They should be equal because the forces treat these particles the same. But what we found actually is that they're not equal. And this led, in March of last year, the experiment released results showing for the first time evidence that these two decay processes weren't happening at the same rate. And it actually got quite big coverage. It was on BBC television news, and there was articles all over the press. It was quite exciting, and it was sort of strange in a way, because it's probably, even to you, and I've tried to explain it as best I can, but it probably sounds a bit technical. Two decays that are a bit different, well, you know, who cares? I mean, the reason this is a big deal is that the only way to explain this, if it's right, and if it's not a mistake in the experiment, which it could be, there's always a chance we've made a mistake, because they're quite complicated, these things to measure. But if it's not a mistake, then this is evidence for the existence of a new force of nature. And we haven't discovered a new force of nature for about 100 years. So that would be a pretty big deal. And it could well be connected to this story that I've been trying to share with you this evening, the story of where matter comes from. It could be the first little chink of light from a door that we can prise open and walk into a new sort of room with new objects in it that will help us understand the ultimate origins of matter. I really hope this does bear out. This is actually the area that I work in. I produced a measurement myself in October last year where we see a very similar effect. So the evidence is gradually piling up in favor of this picture. So it's still, I have to say, with a big caveat, it's still too early to say, but we could be on the brink of something really exciting. So that's the end of the talk. So I'm sorry I didn't actually tell you how to make an apple pie from scratch. I mean, if you can get back as far as quarks and gluons, that's pretty good going, I think. I mean, you can't buy them in the shops, unfortunately. But yeah, as I said, this story isn't finished yet. It's still, this is where sort of modern physics lives. We're trying to answer these remaining questions and continually pushing back closer and closer to the moment of the Big Bang. And I hope in the future we'll have some more exciting news to share with you. But I'll just finish by saying I hope you've enjoyed the talk, and if you have, I encourage you to buy the book, and I'm very happy to answer your questions. Thanks for your attention. Thank you. Right. Oh yes.
Could you just touch on one of the other things that isn't explained by the standard model, which I understand dark matter?
Yes. So yeah, I mentioned two of the problems, basically because they're related to the recipe, effectively. But yeah, there are lots of other problems. Dark matter is probably the most embarrassing of all of them. So we've got these two problems that say we shouldn't exist. The other one is we don't really know what the universe is made from, it turns out. Thanks to astronomers who keep causing us problems, we now know that about 95% of the universe is invisible. And it's made of two substances, one called dark matter and another called dark energy. So dark matter, the way the dark matter was the first real evidence for dark matter came from an American astronomer called Vera Rubin, working in the 1970s. And she was looking at the orbits of stars around galaxies, like Andromeda. Andromeda is the sort of nearest large galaxy to the Milky Way. And what she found, she was measuring the speeds with which these stars orbit. And what she found was that the stars are moving too quickly around their galaxies. Basically, they're going so fast that the gravity of the galaxy shouldn't be able to hold on to the stars, and the stars should all drift off into space. And this was indirect evidence for the existence of some invisible matter that was providing additional gravity, basically holding the galaxies together. And this is what we call dark matter. So whatever dark matter is, and we don't know what it is, the reason it's called dark matter is it doesn't emit or absorb or reflect light. So invisible matter would probably be more an appropriate name for it. And the evidence for dark matter's existence is overwhelming now. There's huge amounts of evidence from all kinds of areas of astronomy. It's a key ingredient of the Big Bang model. The Big Bang doesn't really work without dark matter. So we're more or less as close as you can be to being sure that this stuff is out there. And there is no particle in that table I showed you, no particle in the standard model that can explain what dark matter is. So this is another really key clue that there's more to be found. And there have been many attempts to detect dark matter, and there are lots of different ways of doing it. One is the Large Hadron Collider. You hope that you might be able to make a dark matter particle in your collision. This is a bit of a problem because it's invisible, so you don't actually see it, but what you do see is something missing. So you basically see some visible stuff over here and nothing on the other side. You go, oh, okay, maybe there was some dark matter. That, unfortunately, so far at least, there's no evidence of that, but maybe we'll see some still in the coming years. There are other experiments that are buried deep underground, often in mine shafts, where you have essentially big vessels full of liquid gases, got very low temperatures. And what they're doing is waiting for presumably if dark matter's out there, it's drifting through this room and through the Earth all the time. They're waiting for a dark matter particle to bimble along and bump into an atom and give off a little flash of light. But again, those experiments still have not found any evidence of dark matter. So we have, so we have this problem, which is dark matter makes about 27% of the universe. Atoms and stars and basically everything that we are and everything we see is only 5%. And then there's something else called, even more mysterious, called dark energy. And dark energy, it makes up 68% of the universe, and we really don't know what that is. It's basically some kind of repulsive energy that is making the universe expand at an accelerating rate. But it's really just a word at the moment. It's a word for something, and we have no idea what it is. Well, we have ideas what it is, we have absolutely no evidence for what it is. So I guess the takeaway is that there's a lot still to find. We've only really scratched the surface in a lot of ways. 95% of the universe is still terra incognita. Yeah.
The changes that you're seeing in the experiments which you've recently been doing, are those necessarily proof of a new force at play, or could they be maybe a Fermi field or something else?
So they generally have to be a new force, yes, because of, this is a sort of technical point, but forces, actually, let's not get into spin. But yes, basically, short answer is yes, that it does have to be a new force on the whole, the most popular theories anyway. So, as I said, because the force and standard model, they're the things that mediate these decays. They treat these electrons and muons the same. So what this is presumably is some kind of force that treats electrons and muons differently. And the reason this is sort of exciting, actually, I don't know if I can get back to my standard model picture. Oh, there we are. Yeah. We have this weird unexplained fact. These particles, they come in what are called generations. So we have the up and the down quark here. That makes up the nucleus of an atom. We have the electron. And then we have something called an electron neutrino. Most of the universe is made of just these four. But for reasons we don't really understand, there are two additional copies of these particles. So you have these two extra columns in the table where the particles have exactly the same properties, but they're just heavier. So you have the muon, which is the heavy version of the electron, for example. We do not know why there are two extra columns. But we think if there is a force that treats these different generations differently, it's probably connected to why those generations exist. So it's more than just a new force is cool. That's not, we all like to discover a new force. But the thing that would be really interesting about it is it might start to explain the structure of the standard model itself and may give us a deeper understanding, a bit like the way the discovery of atomic structure explained the periodic table. So yeah, it's a force, we think, if it's real, and it's not a mistake. Yeah.
What did your journey from GCSEs to where you are now consist of?
What did my journey from GCSEs to now consist of? Well, as you really want to know, I did double maths, physics, chemistry, and history, which was fun. And then I went to university and I did a degree called Natural Sciences, which is a kind of mixed science degree where you do maths and 3 sciences in your first year. So it's the way quite a few universities do this course. Cambridge does it, for example. And then basically, I was saying this actually to some of the students earlier, physics at school and university are quite different subjects in a lot of ways. Like at school, physics is there's a bit more sort of rote learning. You do a bit of problem solving, some mathematics, not a huge amount though, because you can't necessarily assume, I guess, the students have a high enough level of maths. When you get to university, it becomes much more mathematical, and some people hate that, and other people like that. And I found that was where I got really excited. I didn't really have any intention of being a scientist when I went to university, but when I got there, I really fell in love with the sort of problem solving aspect of it, because it becomes much less about learning facts and much more about, here are a set of laws or a set of rules, can you figure out the consequences of them? So I found that it can be both infuriating. You can spend hours banging your head against a problem and not being able to solve it. But it can also be, when you do solve it, it's really rewarding. So, so I suppose I sort of really fell in love with physics. I always found the ideas in physics exciting, this sort of stuff, But also getting to grips with the theory was really enjoyable. And then I did a summer studentship at CERN. CERN ran this summer student program for people in their undergraduate or third year usually. So people from all over Europe come together and you spend about 2 months at CERN doing a project and getting some experience. And then after I did a PhD and I've never left. I've sort of, it's slightly terrifying. I think this year I've been at Cambridge University for half my life, which is, I remember looking at my old professors when I was a student thinking, who'd been there for, 40 years or something, that's not going to happen to me, but it is scary, it is happening. Anyway, so that was the path. But I didn't have a particular plan. It was sort of, and there were quite a few points where I could easily have gone in a different direction. But it's really, I suppose the reason I've stuck with it is because I found it exciting and enjoyable. And I've been also very lucky to work at a place like the Science Museum. I think, part of the reason I do these sorts of events and talk to people about science is because it keeps my own excitement about the subject alive.
I'm not sure if I just read it wrong, but back earlier towards the start, the color-coded periodic table of different origins of the elements, and it looked like some of the heavier elements, gold platinum, had a bit showing that they were partially made, yellow, which shows dying low mass stars, which, how would that be possible if they only made up to like carbon and nitrogen previously? How did it make that whole fluid be heavier towards the bottom, at least partially?
That's a bloody good question. Honestly, I don't know. Not being a stellar nucleosynthesis person, but I would guess it's probably that they are made from so probably what happens, I think, is that stars like our sun, which are third generation stars, they basically contain all of the elements because they've been made in earlier generations of stars. So they will contain, for example, platinum and gold and iridium and osmium and so on. And I think in the red giant stage, I'm probably going to get this wrong, so maybe I'm going to check on Wikipedia or something later. You have reactions between hydrogen and elements. So basically there's reactions where a hydrogen atom can be swallowed by a heavier element. So I think what's probably happening, say for gold, is that a platinum nucleus is absorbing a proton and being promoted up the table by one step, or possibly absorbing a helium nucleus and going up, from a sort of lower position. So it's not that I'm convinced it won't be that they're being made from hydrogen or from the basic elements, but it's probably that they're being moved along the table by a small series of small absorption processes, I think. But you go and ask a proper expert.
Dr. Cliff, on behalf of everybody here, I'm aware of the time, and I know that lots of us will need to be getting home this evening. But on behalf of everybody here, thank you so much for a phenomenal talk.
Thank you.
Another sense in which you spoke about a story, and the idea that the story is being constantly rewritten and added to. And I think that's a really, really lovely analogy. And I think keeping an eye on this and watching it and seeing the headlines that are coming through constantly just makes the story continue and makes it even more exciting as you learn more about it. So thank you very much for all of you've done here. I would like to counter the apple pie with a Richard Feynman quote, which was genuinely the pleasure of finding things out. And I think that talk sums it up, that quote sums up what we've heard here really brilliantly. So thank you very much to yourself. Thank you very much to everybody who's here, and particularly for our guests, and also for those who've actually made this possible. Because a lot of time and effort goes into organising these things. But for us, we'll take them thanks to Harry.
Well, thank you very much. That's very kind. Thank you.
Talk.
Thanks.
If you'd like to join me in the final round of applause.
Thanks very much.
This auditorium, as full as it is now, is an indication of the kind of demand that we have for talks like this, then I'm absolutely sure there'll be more. And the Peake Lecture series will continue. So please do keep an eye out for that. But it leaves me just to say thank you everybody for coming and have a very safe journey. Thank you.
Thank you. Thanks very much.